Good, then let's start with statistics for data science with the last lecture before the Christmas break, and actually also the last lecture in this series of lectures on basic probability theory. The topic today are inequalities and limits, and we will focus on some results relating to inequalities and limits, and these will be presented in the context of probability theory, but they will have immediate consequences and applications in statistics. So basically everything that we do today will be revisited after the Christmas break, once we talk about estimator properties. So once we have established what it means to estimate a parameter of a parametric statistical model, we will ask ourselves the questions as people who do data analysis do or should do, whether the results, the parameter estimates, the trained parameters, whether they make any sense. And there's of course a whole theory on estimator properties in statistics, and the basic results there follow directly from the results in probability theory on inequalities and limits. So although it may sound today a little bit like another topic in probability theory with no direct connection to data analysis, this is completely not the case, but of course can only be appreciated once we actually discussed estimators and their properties. The material here is of course not a full and comprehensive overview. I focus on these things, on those inequalities and limits that we will need further along the course, and of course you find all of this in the typical books that we are using, so the Wassermann book, the Casella and Berger book, and of course the de Groot book. The plan is then as follows. So I think in the first hour I want to discuss the inequalities, and I structured them into probability inequalities. So these are statements about inequalities relating to probability, and expectation inequalities, which are of course then inequalities relating to expectations. And after the break, in the second hour this morning, I would like to talk then about laws of large numbers and and central limit theorems, so the limits aspect of this lecture. And in the exercises we will today focus and only consider programming exercises. So we will have 3 presentations, I believe, and I might show you a little bit more regarding my implementations of the inequalities to then appreciate what they mean from a more applied or more concrete perspective. So that's the plan. Then let's go. And there is no particular there is a little bit of a hierarchy in terms of the inequalities that we discuss, but it's not that we start with a great example or something like that. We will basically work our way through the inequalities of interest that we will need. Which means that we start straight away with one basic inequality, namely the so-called Markov inequality. This Markov inequality states that if we have a random variable x which takes on values larger or equal to 0 with probability 1, then it holds for all real values x that the probability that the random variable x takes on a value larger or equal to some real value x is smaller or equal than the expectation of the random variable divided by that value that we are evaluating with respect to its exceedance probability of the random variable x. So these probabilities of x taking on values larger or equal to a number x are also referred to as exceedance probabilities. And in this sense, the Markov inequality relates exceedance probabilities and expectations, which is fairly obvious. So here we have an exceedance probability, here we have an expectation. An example for an instantiation of this inequality maybe is that if we have a random variable with expectation 1, which fulfills this probability of x is larger or equal to 0, being 1, then the probability that the random variable x takes on a value larger or equal to 100 is smaller or equal to 1 over 100, yeah, because the expected value or the expectation is just 1. And I mean, that's quite a statement if you want, because with the expectation, as we learned last time, we have just a one number summary of the distribution of a random variable, and regardless of the form of the probability distribution, so of course try not to think always just of the Gaussian, but of some arbitrary maybe probability density function that integrates to 1 but has its bumps and everything everywhere, it cannot be that the probability that the random variable x takes on a value larger than 100 is larger than 1 over 100 if the expected value is 1 and if the random variable takes on values larger or equal to 0 with probability 1. So that's the Markov inequality, which is kind of the basic inequality on which other inequalities will build. How can we show this? So we consider a continuous random variable here with PDF P, and then we learned last time that the expected value is given by integrating the values of the random variable from -infinity to infinity, multiplied by their associated probability density. And of course we can split up this integral into a part that goes from -infinity up to the value a value x that we are interested in, and another part that starts with the integration lower boundary at this value that we are interested in and goes up to infinity. So we're just splitting up this integral over the entire real line. And then we have the following inequalities. If we assume that the probability of x being larger than 0 is 1, then the expected value is larger or equal to this second part here, because the rule for positive, so the negative will not cancel out, and for positive x's we always have positive probability values. So we can only consider this second part. So if you want, you can also just think of x as positive things here, and then we can neglect this part and have that the expectation is larger or equal to then this part. This then is this expression. This expression here is larger or equal to considering the same integral only with respect to x, not the integration variable. So we fix x here at the lowest value, and because we fix it at the lowest value, this is obviously larger than this. And once we do this, we can take our x out of the integral with the linearity property of integrals, because it's a constant, and then we have here the probability of x being larger or equal to a value x, and have here this multiple x in front. And then of course we have this inequality, and we can just divide by x and get the Markov inequality. So yeah, I mean, one way to think about it is that the probability for all negative x's is 0, and there's only positive probability for a positive axis, and then this makes immediate sense. Here is an example, so I implemented that, and maybe then later in the exercise we can also look at the code, but in a way, I have a tendency to understand things a little bit better if I write code for that. So here I used a chi-square distribution with n degrees of freedom, which has expectation n, so the expected value or the expectation here of this chi-square PDF random variable is 10. And what I plot here is the probability for the random variable to take on a value larger than some x. Of course, this is 1 minus the CDF of this chi-square random variable, which we can of course evaluate with, for example, SciPy-Stats. And so I plot this. I also, I don't know, for some reason like to confirm this via sampling. So I sample this chi-square random variable and evaluate the probability, or estimate the probability. This should actually be, there's a typo here. That's is hat p. I still need to figure out how to use the amsmath package in matplotlib so that I can use these commands, which I currently can't use. So I actually want to use, what I actually wanted to have here is this, but I wasn't able to. So this is estimated, so from a random number generator, and compared to the analytical counterpart. And what I then plot here is the right side of the Markov inequality, so the expected value divided by the respective value of x. The expected value of course stays constant, and x always increases, so this goes down. But you can see that in this scenario the expected value divided by x is always larger than the probability for the random variable x taking on a value larger than the small x. So that's kind of a visualization of the Markov inequality if you want. Good. So that was the Markov inequality. In essence, the Chebyshev inequality is a direct consequence of the Markov inequality. So whereas the Markov inequality talked about expectations, the Chebyshev inequality considers variances, which of course are fairly related to expectations, as we learned last time. So what does the Chebyshev inequality state? If we have a random variable x which has variance vx, then for all real values it holds that the absolute value of the deviation of the random variable from its expectation, the probability of these deviations of the random variable from the expectation is larger or equal to x. This probability is smaller than the variance of x divided by the square of x. So again, we have a statement here about the exceedance probability. So the probability of an absolute value of a deviation of the random variable from expected value, and the exceedance probability is with regard to some real number, and this probability is always smaller than the variance of the random variable divided by x squared. So we are relating here exceedance probabilities of deviations from the expected value to the variance of the random variable. Now, and of course this makes some sense with regard to the Markov inequality, where we just had exceedance probabilities, and here we are then talking about exceedance probabilities of deviations from the expected value. So how far a random variable takes on values far away from its expected value, and of course intuitively this is related to the variance of the random variable. Yeah, this is what I just said. One interesting feature is if one sets this x here to 3 times the square root of the variance, I think you could also set it to not 3 times the square root, but anything else, then you actually get a number. So the probability for the absolute value of a deviation of the random variable x from its expectation to be larger than 3 times its variance is 1/9, which just results from plugging in this value on the right side here as x and squaring it so that the variances cancel out, so you get a number. So if you put in for the x, we put in the square root of the variance, then you get concrete numbers. How does that follow? It follows from the fact that first, if we have real numbers, then the inequality that the square of a is larger or equal to the square of b implies that the absolute value of a is larger or equal to the absolute the absolute value of a is larger or equal to b. This kind of implication will actually feature multiple times. So I think you should make sure that you have a good feeling why this holds. So I think the best way to think about it is if you take a to be a positive number, and then you consider the case that you put minus a on the left hand side, so that you have something negative on the left hand side, then you square, so you get a positive number, and on the right hand side you always square. Then you take the square root, and then you have essentially evaluated the absolute value for this negative number on the left hand side in this equality. And of course, if a is a positive number all along, then it doesn't matter. So if we have that, then if we set in the Markov inequality, and this is where the hierarchical nature of the lecture kicks in, if in the Markov inequality you set the random variable of interest to be this deviation, then and you set in the Markov inequality instead of x, you put in x squared, which of course is just another real number. So again, have a look at the Markov inequality here, and we define now y, and we take our x to be some x squared. Then we get from the Markov inequality this. Then of course we can evaluate y or replace it, which means that we here get the variance, we retain our x square, and here we basically use the fact that a square larger than b square implies that the absolute value of a is larger than b. So the Chebyshev inequality basically extends the Markov inequality to variances, and is also a probability inequality in the sense that it talks about exceedance probabilities. Here is an example. So here I used the Gaussian and looked at a Gaussian with expectation parameter 0 and variance parameter 3, looked at the expectation and the variance, which I plotted here, and then I plotted the probability of the absolute value of the random variable deviation from its expectation to be larger than some x, which of course for a Gaussian is because it's symmetric, is fairly straightforward to evaluate. So the absolute value, of course, this can be either negative or positive, and hence we are looking at the probability that in the positive case x minus ex is larger or equal than x, and in the negative case that this is smaller or equal to minus x, because if we then take the absolute value, we get back here, and the results are then plotted here. So we have the analytical results again is the thick blue line. I also sampled this, as I can show you later, and then I plot also this variance divided by x squared term, and you see that this is then always larger than this than the probability. So we see that in effect this here is larger or equal to this, but here it's actually larger. So these are the two probability inequalities which will feature again. So the Markov inequality relating exceedance probabilities to expectations, and the Chebyshev inequality relating variances and exceedance probabilities. What we also will need further along the course are, I think, two expectation inequalities, and they also the first expectation inequality also, which is the Cauchy-Schwarz inequality, also takes care of this fact that I mentioned last time, that the correlation coefficient takes on values in the closed interval -1 to 1, which I didn't show last time, but which is a direct consequence of the Cauchy-Schwarz inequality. So what's the Cauchy-Schwarz inequality? Schwarz, because I'm speaking English. If we have two random variables x and y, and we assume that that's actually quite bad, because now I'm actually not quite sure what is supposed to exist. So either both of the expectations. So definitely, I think it's about that the expected value of the product of x and y exists. So is smaller than infinity. This is of course ma BB e x y. Then the square of the expectation of the product of x and y is equal to or smaller than or equal to the product of the squared expectations of x and y. So this is essentially a triangle inequality. So if you are happy with triangle inequalities, for example in linear algebra, in terms of dot products, then this is essentially the same thing, because you can of course always view forming expectations also as forming dot products, but that's a whole different story in a way, or it's a whole story. It's not a different story, but it's a whole story. So I will not go deep into this. But there are of course connections between this Cauchy-Schwarz inequality and triangle inequalities in linear algebra. And as I already said, the correlation inequality is a direct consequence of the Cauchy-Schwarz inequality. So where does it come from? Sorry, I didn't put any breaks in here. So there is a full proof in the group book, so I'm not considering some special cases here. This is also why I know that this must be about x, the product of x and y, because in the group book it also considers the case that ex square is can be infinity, so I'm only considering the case where the expectations of the squared random variables actually exist. So of course that they are not zero. This is also considered in the group book, so I also don't look at that. But of course they must be larger than or equal to 0, because we have square operations here. So we only consider this case. So cases where they are infinity or where they are 0 are considered in the group book. It's not that exciting, but you can have a look there if you're interested in these special cases. But if we assume that the expected value of the square of x and y and y square are positive, then for all which doesn't actually follow from this, but we have that for all. This is what confused me actually this morning when I looked at that. We have that for all AB, which are real numbers. It holds, of course, that the expected value of AX plus B y and the expected value of AX minus BY, both of them squared, is larger or equal to 0. This just holds because we have a square here, and squares have a tendency to be larger or equal to 0. And if we take the expected value, of course, of just non-negative numbers, we also get something non-negative. So this follows just naturally by the square. These things imply the following. So if we resolve the brackets here, we get the inequalities that a square times ex square plus b square y square plus 2ab exy is larger or equal to 0, and the same thing with the minus sign from this. And then we can get to the Cauchy-Schwarz inequality by setting these numbers a and b to the square root of the expected value of y square and the square root of the expected value of x square, respectively. And then substituting for our a's and b's in these two inequalities. So if we substitute for a in this inequality, we substitute square root of the expected value of y square, then we get this expression where now our a's and b's, actually we also substitute the b here, our a's and b's are gone, and we have just expected values of the random variable squares. And then we can reformulate this or take things to the other side. So we take this over here and have twice this. Then we can divide by 2 and take square roots, and then we end up with the fact that the negative expected value of xy is smaller or equal to the square root of the expected value of y square and x square. And if we of course square that, then we have our Cauchy-Schwarz inequality here for the case that we have a negative number here. And then we can do actually the same thing for the case that we use this and get the positive case. So that's one way to show the Cauchy-Schwarz inequality. Essentially, this whole thing is based on the fact that squares are non-negative, and then selecting, defining in linear combinations of random variables, defining the linear coefficient according to this, and of course using the I have to actually guess. This is one of the results that we showed last time about this is nothing about the results of last time. This is just linear combinations of random variables and their expected value. Sorry, I was just confused there because I was thinking about something about variances and -2 the covariance, but this is not this. Sorry. Yeah. So that's the Cauchy-Schwarz inequality. I wanted to have a little bit of a closer look at it. I don't know how helpful that is. Once I did it, I wanted to have a closer look at that for the case of the bivariate Gaussian. So I looked at bivariate random vector xy and with a bivariate Gaussian, and evaluated the expected value of xy squared, which one can do from the covariance translation theorem, and then also looked at the expected value of x square and y square, which one can get from the variance translation theorem, and then stated the Cauchy-Schwarz inequality for this bivariate Gaussian, which then states that the square of the covariance of x and y plus the product of the expectations is equal to or smaller than the square of the square of the variance of x plus the square of the expected value of x times the same thing for y. And I don't know, yeah, one can plot this and one sees that the right hand side is always larger or equal to the left hand side if one varies parameters. In the end, I didn't find this too helpful. It makes things a little bit more complicated than I hoped it, or maybe not more complicated, but it doesn't make it more intuitive, I found. I mean, you just evaluate these expressions analytically and then yeah, it holds. So this we don't have to look at during programming. This is, however, an important consequence here of the Cauchy-Schwarz inequality. If we have two random variables with variances vx and vy, then the square of the correlation or the correlation coefficient, which is of course the square of the covariance divided by the variances of x and y, is smaller or equal to 1. Oops, sorry. Which of course implies that the absolute value of the correlation coefficient is smaller or equal to 1, because if it's negative and we square it and then take the square root, we get the absolute value. If it's positive, it holds anyway. So this then implies that the correlation coefficient is always in the closed interval from -1 to 1. How does that follow? That follows quite straightforwardly by setting in the Cauchy-Schwarz inequality, setting the random variables to be the deviation of x from its expected value and the deviation of y from its expected value, and then putting these definition into the Cauchy-Schwarz inequality. We already have on the left hand side the covariance squared, and on the right hand side we have the variances, the product of the variances. So again, if we have the Cauchy-Schwarz inequality and we put in x minus its expected value for the random variable y, and we put in y minus the expected value for the random variable y, then we have the variances on the right hand side and the covariance on the left hand side, and then we already have the correlation inequality. And yeah, the correlation inequality will feature quite prominently. So this will, if I'm not mistaken, if I remember correctly from last year, which was the first time that I taught this course with these kind of contents, this is closely related to the the thing that we will, it has Rao is one of the names, which will be quite crucial for statements regarding the variance of estimators. Yeah, it's also time for me to take a Christmas break. Finally, the last inequality that I want to discuss, which we will need occasionally, and which for me always relates to Bayesian stuff, which is also an expectation inequality, is Jensen's inequality. So we are now leaving the Cauchy-Schwarz inequality. So this thing, we're leaving that behind and go to a new inequality, Jensen's inequality, which talks about the expectations of functions of random variables which are either convex or concave. So if we have a random variable x and we have a convex function, so a function for which this holds, so if you form the convex combination of the values in the domain of the function, so you take lambda x1 plus 1 minus lambda x2, then for a convex function, the values that are transformed here are always smaller or equal than the convex combination, or the do you want to say convex combination? The convex combination of the values that the function takes on, so lambda gx1 plus 1 minus lambda gx square. In this case, if we have a convex transformation of a random variable, then the expected value of the convex transformation of the random variable x is always larger or equal to the convex transformation of the expected value of x. And if you want the reverse holds for concave functions. So if we have, don't want to call it convex combination, I want to call it somehow looking for the word here. If we look at this combination again in the domain of the function, and if the transformation of that is always larger than the combination of the values that the function takes on, then the reverse holds true. So then the expected value of the concave transformation of x is equal to or smaller than the concave transformation of the expected value of x. And again, convex functions are functions for which the graphs lie above the straight line from two values in the function value space. And for concave functions, that's reversed. What the Jensen's inequality specifically in things like variational inference is crucial for is if the transformation g is the logarithm, and the logarithm is a concave function. So think of the logarithm, which makes this kind of has this kind of graph, and then if you put a straight line, that's always below the functions graph. So the function graph is always above a straight line connecting two points in the function value space, and hence the expected value of the logarithm of x is always smaller or equal to the logarithm of the expected value of x. And that's relatively straightforward to show, so I'm only considering the concave case here, which is also more important in terms of statistics. So if we consider f to be a tangent line at the point of the transformation of the expected value, that is, we have a linear affine function of the form ax plus b for some a and b, then we if this is a tangent line, then f of the transformation of ex equals g of ex, which just holds because it's a tangent line. Because g is a concave function, we have that g of x is smaller than ax plus b for all x, and hence also the value of g for the random variable is smaller or equal to ax plus b, and hence our expected value of the transformation of x is smaller or equal to the expected value of our linear transformation here, and then we can evaluate the expected value, and this is so what we're doing here is essentially we are using the concave property and considering the considering a linear transformation, which we have already defined to be the tangent line at g of ex, and then we have seen, because of the concavity, we have that the expected value of g of x is smaller or equal to than the transformation g of the expected value of x. I think a drawing would be nice here. I think I guess I said the same thing last year. Maybe then next year. Good. So these were the inequalities that we need. So again, let's briefly focus on the results. So we have two probability inequalities, the Markov inequality, stating something about the exceedance probability with respect to expectations. We have the Chebyshev inequality, stating something about the exceedance probability of absolute deviations from the expected value and variances. And then we have the Cauchy-Schwarz inequality, stating something about the squares of expected values in products of random variables. A direct consequence being the correlation inequality, which states that the correlation coefficient is always between or equal to -1 and 1. And finally we have Jensen's inequality. So essentially we only have 4 inequalities: Markov, Chebyshev, Cauchy-Schwarz and Jensen, and correlation inequality is just a special case of Cauchy-Schwarz. Okay, so that was what I wanted to do in the first hour. Any questions, discussion points, typos? Okay, then let's take a break and then leave the realm of inequalities behind for the moment. We will get back to these inequalities and always refer to them once we discuss estimator properties, and then in the second hour talk about what happens if samples get large, or in probability if we have very many random variables. So let's take a break until 8:30. Okay, then let us continue with the final hour of the lecture before the Christmas break, which relates to laws of large numbers and central limit theorems. And the statistical intuition here is, of course, what happens if samples get large, so big data. So this is our first exploration of big data questions in statistics. And yeah, let's go and start with laws of large numbers. And for both limits classes, so laws of large numbers and central limit theorems, I put up an overview first, which basically just states what's going on, and then we can look at the math. So intuitively, both the weak and the strong law of large numbers state that for IID random samples of a distribution, the sample mean approximates the expectation of that distribution for large sample sizes. So that's something that of course we already in a way used intuitively or heuristically when we defined the expected value. So in the definition, of course, that did not feature, but when I then gave you an interpretation of what that is, I already said that this is something like the sample mean for large sample sizes. There are two forms of that in the literature which differ in terms of the random variable convergence that is considered, and that's something that you find everywhere, so it makes sense to know about it. So the limit theorems that we will encounter relate closely to three forms of convergence of random variables. So I hope all of you are somewhat familiar with convergence in analysis, where you consider that for sequences or for series, and then for functions where you have things like pointwise convergence. And these kind of convergence concepts also exist in probability, where of course we have random variables which are functions. So if we consider sequences of random variables, we always consider sequences of functions, and then these functions converge to another function, namely another random variable, which may or may not be constant. And then there are different forms of these convergences. And we will need convergence in probability and almost sure convergence for the laws of large numbers, and then we will need convergence in distribution for the limit theorems. So first, what is convergence in probability? That's defined as follows. A sequence x1, x2 of random variables is said to converge to a random variable x in probability, for which we write that these xn go to x as n goes to infinity, and this p means that we have a convergence in probability. If for every small, in brackets, epsilon that is larger than 0, the limit of the probabilities that the absolute value of the deviation of xn from x is smaller than epsilon equals 1. So this is a statement about probabilities. You can imagine that we have many probabilities that depend on n, and we look at the probability that a random variable the absolute value of this random variable deviates from the target random variable to which all of these converge. Then the probability that the absolute value of this deviation is small and increasingly small, so you can make epsilon arbitrarily small but larger than 0. Then the limit of these probabilities is 1. One can easily reformulate this using essentially linearity of limits by stating that the probability that the absolute value of the deviation between a random variable and a target random variable is larger or equal to epsilon is 0. So if n gets large, stated very straightforwardly, if n gets large for a sequence of random variables that converges to a random variable x, then the probability that an xn with a large n deviates from x is vanishing. So here's different ways to express that. So this typo. The statement that a sequence of random variables xn converges in probability to x means that the probability that xn lies inside the random interval x minus epsilon, x plus epsilon, no matter how small this interval may be, approaches 1 as n goes to infinity. So as n goes to infinity, the probability for xn to deviate from x gets to 0. And if the random variable that the sequence of random variables is converging to is actually a constant, so a number, which is of course also a function, it's just a constant function, this means that the probability distribution of the xi becomes increasingly concentrated around this constant value. So as n gets large, you hardly find any deviations, or you hardly sample any deviations of xn from this value. So that's convergence in probability. And convergence in probability is essentially if you apply it to a specific sequence of random variables, namely a sequence of sample means, then convergent probability is exactly what the weak law of large numbers says. So for the weak law of large numbers, let x1 to xn denote a random sample from a distribution with expectation mu, and let bar xn denote the sample mean of n random variables xi. Then bar xn converges to mu in probability. Intuitively, this means that the probability that the sample mean is identical to the expectation of x of the xi approaches 1 as the sample size gets large. So for large sample sizes, the probability that the sample mean equals the expectation of these random variables, which of course all have the same expectation, this probability is 1. So and very intuitively, if you compute the sample mean of a very large sample of random variables, then you will recover the expected value of the random variables. Here's a simulation. We will also look at a simulation and the code in the presentation today. So what I did here is sample standard normal random variables, and then increased the sample size and computed the sample mean, and estimated the probability that the absolute value of the sample mean deviates from the expected value, which is 0. So I could also basically leave this out here because mu is 0 anyway, is larger or equal to some epsilon. And of course this depends on the epsilon. So how fast this goes to 0, because we are interested in this going to 0. So we are looking at this part here, and you can see if we consider an epsilon which is relatively large, then the probability for this sample mean for the absolute value of the sample mean to exceed this epsilon is going down quite quickly. If our epsilon is smaller, then it's not going down that quickly, but it's still going down. And if we have an even smaller epsilon, then it takes longer. So we need larger samples for very small deviations not to occur anymore. But eventually, and this is what the weak law of large numbers says, eventually they don't occur anymore. And we will look at an implementation of that later on, as I said already. There is a stronger form of the law of large numbers, which relates maybe a little bit more to the notion of random variables as functions. We will not need that much, but I stated nevertheless. So a sequence of random variables converges almost surely to a random variable x, which we write as xn goes to x as n goes to infinity almost surely. There could be a s dot. If the probability of the limit of the absolute value of the sequence of random variables to deviate from x, sorry for that, that must be x here, equals 1. So the crucial difference, or the most striking difference between convergence in probability, and almost sure convergence is the relationship of the probability and the limit. So here we're talking about a limit of probabilities. So we have a limit and we're looking at the probabilities of xn minus x. And here we're looking at the probability of a limit. So that's the main difference. So here it helps to think a little bit again about the basic probability model. So our random variables are functions, and we have, if we consider our functions from the elementary outcome space to the outcome space of the random variable, then we can also consider a subset of the elementary outcome space, which is referred to as a null set, which has a probability of where elements have a probability of 0 to occur, and then based on this background thinking, then almost sure convergence implies that for all omega that are not in a null set, the xn sequence, if indexed by such a omega, which is, if you want, sampled in the elementary outcome space, converges to our random variable of interest. Yeah. So except on a null set of elementary outcomes, this pointwise convergence of function sequences is holds. And what one can do, and what you find in the books, is to study the relationships between convergence forms. So one can show that almost sure convergence implies convergence in probability, but not the other way around. So it's stronger. We omit these things. I mean, that's yeah. One can go really deep in there and study all the relationships, and for certain things it might be helpful. But yeah, I'm not going very deep in there. So based on this notion of almost sure convergence, one can then state the law of large numbers also in the strong form. Then if we have a random sample from a distribution with expectation mu, and we again consider the sample mean bar xn, then xn converges almost surely to mu. So the sample mean also fulfills the stronger form of convergence in a probabilistic setting to the expected value. So the probability that xn minus x is smaller than some arbitrary small 0 is 1 as n goes to infinity. Yeah, it's not saying that the probabilities go to 1 for this, but it's saying that the probability that this deviation is smaller than some arbitrary small epsilon 0 is 1. No, so that's the stronger form. Yeah, that's the strong law of large numbers. We're still, or I'm still thinking about how one sensibly simulates this, because this one can simulate relatively straightforwardly. So one estimates the probabilities and looks at the probabilities. Here we have just one probability that one essentially wants to estimate, and one has these pointwise convergence of functions. So maybe I find time to think a little bit deeper about this, and maybe also get an idea how to simulate that. But for the time being, I don't ask anyone anymore to simulate this, because I also don't know really how to simulate that. But the weak law of large numbers, that's straightforward, and we see that this afternoon. Good. So the laws of large numbers, again, to emphasize the important things. Essentially, the laws of large numbers say that the sample mean for large sample converge to the expectations of the random variable of which these sample means are formed, and that's essentially it. So this will then also relate, of course, to the qualitative properties of the sample mean as an estimator for the expected value. So sets kind of the basis for that. Maybe a little bit more exciting than the laws of large numbers, which you could also view as kind of justifying to consider the expected value because they relate nicely to sample means, are the central limit theorems. And so that's our last topic then for this morning. And there are different forms of the central limit theorem. Essentially, what the central limit theorem says is that the sum of very many independent and arbitrarily distributed random variable is normally distributed. So the crucial thing is here, if we look at the sum of random variables or the average, then this sum of random variables is in the end normally distributed. So whatever the distributions are, we end up with a normal distribution. And depending on the proof and the specific author who wrote that, there are different versions. So the Lindenberg and Levy form only assumes independent and identical distributed random variables. So here we have just random variables which are independent and identically distributed. They can have any distribution, but they all need to have the same distribution, and they need to be independent. And in the Lyapunov form, one only needs independent random variables, but they don't need to be all identically distributed. So that's kind of the intuitive form. So if we sum very many random variables, then we get the Gaussian. And of course this is a strong motivation for using the Gaussian as the distribution of errors in statistical models. So for example in linear statistical models, or as we will then look in frequentist statistics, to assume Gaussian errors makes sense from the perspective that of course we don't assume that each of the contributions that we have to our data are Gaussian, but we assume that there are many more contributions to our data that don't have that can be of any kind. And of course we are not saying, if we use the Gaussian assumption, that things are really random. We are just so we don't really make a claim about whether the universe is stochastic or not, but we model all of these contributions that our model does not capture in its deterministic part. We model all of these using a Gaussian, because if there are really many things that we are not considering, if we sum all of them up, then we actually get a Gaussian. So the Gaussian, so the central limit theorem is a good justification for using the Gaussian as a distribution of errors in statistical models. So for the central limit theorem, we need another form of convergence, and the convergence that is used in no, gradient descent is not. So there was a question on gradient descent, whether this has to do with central limit theorem or strong laws. Gradient descent is in the very basic setting has nothing to do with probability theory. That depends on what form of gradient descent in which context one looks at. So central limit theorems need another form of convergence, namely convergence in distribution. and also the notion of an asymptotic distribution, which is also something that will come up quite often in the second part of the course when we talk about frequentist statistics, because we will often look for hypothesis tests or confidence intervals at asymptotic distributions. What is that about? So a sequence of random variables converges to a random variable x in distribution if the limit of the cumulative density functions, or no, sorry, the cumulative distribution functions, I should say, so the CDFs, is the same as the CDF of the random variable x, which they are converging to at all points where the CDF is continuous. The distribution of x is then referred to as the asymptotic distribution of xn. But so in contrast to the convergence in probability, which is a statement about limits of probabilities, or almost sure convergence, which is a statement about probabilities of limits, we are talking here about the limits of distribution functions. So we're talking about a specific form of functions, namely distribution functions, and they converge, or if some sequence of random variables converges to a random variable in distribution, then the corresponding cumulative distribution functions converge to the target distribution function, which is then called the distribution function of the asymptotic distribution of xn. So it's a statement about the convergence of CDFs, and again one can it's actually a relatively weak form of convergence because it's already implied by convergence in probability, and as convergent probability is implied by almost sure convergence, but not the other way around, then almost sure convergence also implies the convergence in distributions. Again, these things can all be proven, and you can study them in the books, but it's just crucial for appreciating here in this context that in these forms of convergence are different. So based on the notion of convergence in distribution, we are of course interested in, if we talk about central limit theorems, in the fact that the target distribution or the asymptotic distribution is Gaussian, so we're interested in the cumulative distribution function of the Gaussian, and then the central limit theorem can be formulated as follows. If we have n random variables and they form an independent and identically distributed random samples of size n from a given distribution with expectation mu and variance sigma square, then for each x, the limit of these probabilities, namely the probabilities of xn minus mu divided by sigma divided by n or square root of n, to be smaller than x, equals the cumulative distribution function of the standard normal. So of course we also have here a limit of probabilities, but these probabilities are specific probabilities, namely exceedance, sorry, not exceedance, but the probabilities that are involved in CDFs, so CDF probabilities if you want. And the crucial thing here is what's going on. So that's always the crucial thing. So we have n independent identically distributed random variables. We form the sample mean. We subtract from the sample mean the known expectation, and we divide by the standard deviation and multiply by the number of samples. And then this expression, so if you want the Z transformed sample mean multiplied by the square root of the number of samples, this has the same CDF as the normal distribution. And we will also see that so this expression here is approximately standard normally distributed. If we're not using the Z transformation, then the sample mean itself is distributed according to a Gaussian with expectation mu and variance parameter sigma square n, which are the variance and the expectation of these xi. And if we not consider the sample mean but only the sum of random variables, then the central limit theorem in this form also implies that the sum is distributed according to a Gaussian with expectation parameter n times mu and n times sigma square. So these things which I list here, so the original form is this, but if we are not considering the Z transformation and also not looking at the sample mean but rather the sum of random variables, they also imply the convergence to the CDF of a Gaussian. So the asymptotic distribution is still a Gaussian, but the parameters are different. Actually, I remember that last year we will need these forms of convergence, and I actually wanted to write that out. I mean, it's relatively straightforward. You need to basically respect or what you basically need to apply is the Z transformation for Gaussians that we looked at when we discussed transformations, and then the affine linear transformations that we also studied. One could make this explicit, but at this point I just listed. So again, the crucial thing about the central limit theorem in the Lindenberg-Levy form is that the random variables are independent and identically distributed. Here is a simulation. Let me first, as I was in the sentence, discuss the Lyapunov form. Here, the random variables need also to be independent but not necessarily identically distributed. So in the simulation here I looked at gamma random variables which all have the same parameter, namely the alpha and the beta parameter being 1, and then I look at the CDF of the standard normal, which is here the gray line, and I look at estimated, so empirical CDFs for a single random variable and for 5 and for 10, and as you can see from the colors, the larger I make the sample, the closer the estimated CDF gets to the Gaussian. Of course, how smooth that is depends on how many samples I take for estimating each of those points here, and that I think here was 10,000, so for 100,000 it looks smoother, but you still have this quite strong deviation. For example, from if you have a single gamma random variable for these kind of for deviations from the expected value of -1. So these are the deviations. So again, a gamma random variable can only take on positive numbers, but can of course be 0. Its expected value is 1. So you can, the maximum deviation you can have for a single gamma random variable is -1. So and then you have quite a strong deviation from the CDF at this point, which then gets smaller once you get to higher sample numbers. Now, in the Lyapunov form, this identical distribution is not necessary. There are these moment requirements or constraints, so that the third moment of all of them exists, and that this thing here that this limit is 0, we can safely ignore that. But then it states essentially the same thing. It's here formulated, which is it's here formulated by considering the sum of the random variables, the sum of the expected values, and the sum of the variances, and taking the square root. This random variable here then converges, or converges to the cumulative distribution function of the standard normal. And again, this implies the same, virtually the same other forms, namely that if we look at here it's not actually said that no, this is a so it implies other forms as here. So here we have again this Z transformed form, which we also have here. But if we only look at the sum of random variables, then we get a Gaussian with expected parameter being the sum of the expected values and variance parameter being the sum of the variances. So again, these are these reformulations by undoing the Z transformation in this random variable here. And here's an example. So first a fairly conservative example. So I used Gaussians, and that the sum of Gaussians converges to a Gaussian CDF is maybe not that surprising. Here I used the deviations of Gaussians, which in itself are then of course Gaussian. Here I use different Gaussians in the sense that each expected value of a Gaussian is corresponding to its index, so mu I equals I, and its variance corresponds to I plus 1, where this actually goes from 0. This is why I did this whole I plus 1 thing, because I did it in Python. Could also start it at 1, but as you know, index and if you then form this yn, you see that already for very small sample sizes this holds. It's not too surprising because the a linear transformation of a Gaussian is again Gaussian, and of course here you have a linear transformation of a linear finite transformation of a Gaussian. It's a little bit more interesting for gamma distributions, where we see essentially the same behavior as for the Levy-Lindenberg form. Here you use then different gamma distributions, again with the parameters or the alpha parameter index, the alpha parameter depending on the index. So here we have all these gamma distributions that I'm summing up to 100. So these are all different gamma distributions, and then after their appropriate renormalization by subtracting the respective expected value and the variance, we get this convergence behavior to the CDF of the standard normal. So that is essentially all I wanted to do this morning. So the limits, again, loss of large numbers, stating that the sample mean converges to the expected value, and the central limit theorem, stating that sums of random variables that are independent and not necessarily all identical converge in distribution to the normal distribution, where one always has to look a little bit closely, especially if one uses these results in proofs then later on for studying asymptotic distributions of statistics. One also always has to pay a little bit of attention into what form of normalization of the random variable is used and which Gaussian asymptotic distribution this then implies. So whether it's the standard Gaussian, standard normal Gaussian, or 0, 1 parameter Gaussian, or it's the mu sigma square Gaussian, or it's the n mu n sigma square, and so on. That one has to pay a little bit of attention pay a little bit attention, but the overall theme that sums of arbitrarily independent random variables converge to a Gaussian, of course, remains the same all the time. Good. Exercises for then later on, first study questions, basically learning these things and memorizing them. So in programming exercises we will have 3 presentations. So first the weak law of large numbers, then the Lindenberg-Levy central limit theorem and the Lyapunov central limit theorem, with the basic distinction that one of them uses all the same random variables and the other one uses different random variables, of course all of them independent. And once we've done those, I can show you a little bit my simulations regarding the inequalities, and then we are done today with the Übung, so no theoretical exercises. So I guess with the Übung we finish a little bit early, but that's fine because it's Christmas, and if we finish early, maybe there's some remaining questions regarding the entire course up to now, because we are also now finishing the first phase of the course, and after Christmas then get into estimation and classical frequentist statistics.